Hi there, welcome to your lesson on significant figures and rounding. Let's begin with significant figures and a quick definition. The number of significant figures in a result is the number of figures that are known with some degree of reliability. And we will see that in this example in just a moment. So sometimes this depends on the measurement that's being taken. For example, if the length of a pencil is measured with a ruler, whose smallest division is 1 millimeter, we can see here these numbers represent centimeters, but then the little lines are millimeters, then the measurement is only accurate to the nearest millimeter. Okay, so let's say, you can say the length of this pencil is 14.6 centimeters, and you can see here, look, 14, and then if you count the little millimeter lines, 14.6. We can say that to that degree of accuracy, to that level of significant figures, and here we have actually 3 significant figures. We can say that because our measuring tool can give us that information, but we cannot say the length of this pencil is 14.63 because that's beyond what our measuring tool can do for us. Okay, so the length of the pencil can be given correct to 3 significant figures, but cannot be given correct to 4 significant figures. Okay, so here's some rules for significant figures. You should know these for sure. We're going to use them not just now, not in this lesson, not just this unit, but in the entire course. In fact, the way your answers on exams are graded is based on whether you used appropriate significant figures. So let's get this skill down. So first, all non-zero digits are significant. Here we can see a number. These are all non-zero digits. So that number expressed this way has 4 significant figures. 1, 2, 3, 4. Next, zeros between non-zero digits are significant. So here we have another number. We have a non-zero at the front, non-zero at the end, and zeros in the middle. In this case, we do count all the digits still. So this is 1, 2, 3, 4, 5. This answer here is given to 5 significant figures. Next rule, zeros to the left of the first non-zero digit are not significant. Okay, zeros to the left. So look at this. We have this number here, 0.023. In this case, this is not 4 significant figures because these zeros are to the left and there's no other number here. So we only count when the zeros end and the non-zero numbers begin. 1, 2. So this is 2 significant figures. This is very important to remember that for decimals. And finally, zeros placed after other digits, but to the right of the decimal point are significant. So if we have zeros here, see we're beyond the decimal point, we put a 1, then there's zeros. Those zeros count as significant figures. So here we have 3 significant figures. And the reason for that is when we put those zeros there, we are implying that we have measured to that degree of accuracy, that we haven't rounded, that this is what we know exactly, these zeros. Okay, let's look at some more here. So these are the same rules, but shown across a bunch of examples that have just 1s and zeros. So look at this one here, 3 significant figures. This one here, 4 significant figures. Here, remember the rule about zeros to the left, you don't count them, so 1 significant figure. And here, more zeros, but you don't count them, still 1 significant figure here as well. Down here, 1.0, zeros after the decimal we count, so this is 2 significant figures, here's 3, and here is 2, because we're not counting those zeros. And here, if we just wrote 100, it would be 1 significant figure, but once we place the decimal, we're saying we have it measured to that exact degree of accuracy. Therefore, 3 significant figures. Okay, take a look at these 2 scales. One can give, we can see here a weight in grams, but this one here is a more scientific scale. You can see the weight is given in grams, point, and then tenths and hundredths of a gram. So this one can give higher precision, more significant figures, significant figures going into more precise small values. So measuring instruments have limitations. We can see this one is limited compared to this one. No instrument is advanced enough to determine an unlimited number of digits. For example, a scale can measure the mass of an object up until a certain decimal place. Again, we can see that here. Measuring instruments are able to determine only a certain number of digits precisely. So this is kind of where significant figures come from in a way. We have a tool that measures, and we can only measure to a certain degree of precision, and that tells us how many significant figures we can get. Okay, so for these 2 diagrams here, you're given kind of like a ruler And on the other one, it's kind of like this old-fashioned kind of scale where you slide these little weights and they tell you the weight of the object on the scale. So your job is to write the value. What value do you read from here and what value do you read from here in terms of weight in grams? And then state the number of significant digits. So let's try. This one here, if you saw it here, hopefully this one here, 98. And then if you notice here, there's 5 divisions here. So that means each one's 0.2, 0.2, 0.2. And we can see this goes to about 98.4 degrees. Oh, this was like a thermometer scale or temperature scale. So 98.4 degrees Fahrenheit, and that is in 3 significant figures. All right, and how precise is this measuring tool? Let's see. Well, here's the largest weight, 500 grams, and there's another 40 grams, so 540 grams. And on the bottom, we have the smallest values, which are just 10 single grams. So we have 541.5. It's about halfway between 541.5 grams, 4 significant figures. Again, we are limited to the significant figures here and here by the ability of our measuring instruments and how precise they can be. All right, so significant figures in another way is in science, we often say they are the number of digits that are definitely known plus 1 estimated digit. Interesting. Here is like we definitely know 98, and the last one here is a little bit of an estimation. So that's kind of how it works, right? So we said 0.4, but that last one is a bit of an estimation. 98 is known for certain. Over here, again, we knew 540 for certain, we knew 541 for certain, and then once I started going here, we kind of estimated that last value. That's how significant figures work. Okay, let's say we have this situation. A laboratory technician compares 2 samples that were measured as 95.270 grams and 23.63 grams. What is the number of significant figures for each of these? And then, okay, so I hope you said here 5 significant figures and here 4. And then this question, is 95.270 grams the same as 95.27? And I hope you're answering there no, because when we have that extra 0, it is basically implying that we had a tool that can give us that level of precision that we can say it's exactly 0.270. Whereas here we have the 7. Maybe that 7 was a rounding from like a 6.8 or a 7.2 or something, and it was rounded to that, right? Whereas this implies a higher level of precision. So these are different. Okay, so for each of these digits here, determine the number of significant figures. Let's see if you get the rules here. Try it out. Okay, and check your work here. If you got any of those wrong, check carefully here. It describes everyone. Okay, moving on. So now that we've talked about significant figures, there's also the idea of approximation and rounding, which kind of goes with that. So if you have something that can measure to a high degree of precision, we can still round and then decrease the number of significant figures. And that's kind of what this next section is about. So what is the difference between an exact value and an approximate value? Well, sometimes, as in the following examples, we can approximate a quantity. And we talked about in our last video lesson was about this topic, about estimation, approximation. So sometimes we can estimate or approximate because the exact values are not known. Maybe because the instrument we use to take the measurements only reaches a certain accuracy. For example, the approximate area of Ecuador is given as this. Maybe we can't go to higher precision, it's just too hard to measure that kind of thing. Or the present height of the Great Pyramid of Giza is approximately 138.8. Again, we might be limited by how we measure it, or the data we have, or the weight of an apple is approximately 250 grams. Okay, sometimes we approximate a quantity because we don't need to know the exact value. Maybe it is measurable, but we just don't need to know exactly what it is. For example, India's population is about 1.8 billion people, right? We could go to more accuracy, but you know, population data changes so much every day, deaths and births, that we can just approximate it. Or I run for about 3 hours every Sunday. Good approximation. We don't need to be more precise. 3 hours sounds like a good rounded number. Or China's economy grew at an average rate of 10% per year during this period. That's a good approximation. Maybe we don't need more detail. So now rounding. Rounding a number is the process of approximating this number to a given degree of accuracy. So again, we might have something that's very precise to many decimal places, but maybe we don't need it to be so precise. So we round and we kind of limit and approximate the number as a result. All right, so try this. Try to round all these numbers to the number of significant figures that are given. So we have a number that here is given in high precision, but we want to lower the precision a little bit. We want to round it to 2 significant figures. What will this be when you round it like that? And hopefully you tried all of them, and you can see all the answers here. This was 4 significant figures, now it is 2. Since we had a 3 following here, we know the rounding rule tells us we will round down or stay at the 2 here. Over here we had 4 significant figures, we want 2 again, so we want to round this. We have a 6 after this 9 here, so this will be rounded up. So it's 0.29, now it'll be 0.30. You need that 0 to have 2 sig fig. This is a common error made by students. Often make sure you see why that became 0.30. Over here, we had 5 significant figures. We want 3, so we're just going to leave it as a whole number of 415. We see a 0.2, so we round down to 415, not 416. And finally, down here, we want 2 significant figures, but there are 3. So there are 3. We will round it to 2 by rounding this 30. Looking at this 5, we round this 0 up to 1, and there we have it. 2 significant figures. Those zeros don't count, remember that. All right, some more. And here's an exam hint for you as well. In exams, give your answers as exact or accurate to 3 sig fig. If you can get an exact answer, write that down. If you need to round, always round to 3 significant figures, unless otherwise told to do something else. All right, here's another one. A circle has this radius. Calculate the circumference and the area, and write your answers correct to 1 decimal place. So this doesn't say significant figure now, it says 1 decimal place. So it can be more or less significant figures, just 1 decimal place. And just a reminder, the circumference of a circle is found using this formula, and the area of a circle is found using this formula. R represents the radius, which we're given here. Okay, check your work here. Here's our circumference, rounded to 1 decimal place. Here's our area, rounded to 1 decimal place as well. All right. Quick TOK question for you. What might be the ethical implications of rounding numbers? We just talked about rounding, but if we round numbers, maybe numbers are important in some way for whatever reason. Is there an ethical concern here? What do you think? Well, here's some things to talk about. Well, can we hide facts by rounding? If we round things, do we hide the real facts? Like if, for example, there's a pandemic right now in the world, and we have many cases of people suffering and dying, or in hospitals and so on. If we do a lot of rounding with those numbers, are we telling the true story? Also, we need to consider, do we always need an exact answer? What are the advantages, disadvantages of rounding? For example, if you round to the nearest $1,000 or $1 million in large financial transactions, what happens to those huge amounts of money that we rounded away, that we rounded off or added? What does that mean for businesses and so on, or for governments? Okay, here's some more rounding. Round each of these to what it asks you to do. So this number rounded to the nearest 10, and this one to the nearest 100, this one to the nearest 1,000. Here's something to get you started. We know when we round, for example, this number here, 2836, we can either round up to the next 10, which would be 40, or down to the next 10, which is 30, right? The 10s are here, so up to 40 or down to 30. What do you think? Well, that one rounds up because of the 6. How about this one here? To the nearest 100. Well, the nearest 100, hundreds are the 7 here. So we either go down to 700 or up to 800. In this case, this is a 4, so we're going to go down to 700. Last one, round to the nearest 1,000. Here we have 30,000, so we're either going to go down to 30,000 or up to 31,000. So this is a 5, we're going to round up to here. Great, a few more. Round this number to 3 decimal places, 2 decimal places, 1 decimal, and to the nearest whole number. Let's see what you get. Check your work here. Again, I've shown the above and below options. That one rounds like this, like that, and like that. Check those carefully. And I think this may be the last one. We have rounding this to the nearest 0.1 centimeter, this one to the nearest centimeter, and so on and so on. See if you can round those correctly. Again, I've put the 2 options on either side, and you can check how you did there. This is, in general, simple stuff, but a really important stuff. Basic number kind of skills that will take us through the rest of our course. So pay close attention, make sure you got the right answers here. Last one for you. Round this one to significant figures. And check your answers here. Did you do it? I hope so.